welcome to a showcase of JDK Security Enhancements talk. I am Anna, and probably you've seen this yesterday at the keynote. How many of you were yesterday at the beginning at 9 a.m.? Okay. And you got the explanation that I like to dress up from time to time as a vampire. But there's an explanation for this one as well. I love to help different events like this one, and am involved in the program committees of certain events. And that one was when I helped a conference back in my home country in Romania, Volksdays Cluj-Napoca, where we'd had a Halloween thematic and I was a vampire. But I still had a technical talk about troubleshooting Java applications and containers, if I'm not mistaken, in 2019. So I like to dress up, but I also like to code with Java, but also enjoy working with Java and containers too. And in my day-to-day life, I work as a developer advocate in the Java team at Oracle. And, well, I enjoy working with Java and making tutorials or workshops on how you can use or better use Java and talk about Java's features as well. Today's talk, well, is about security. And now getting to the serious stuff. That's a more serious version of me. And you can find me on social media, on X and on Mastodon. And you can reach out to me there, ask me questions about what I'm going to present today on security or about Java tools, because I love to talk about those as well, or Java in general. Yet. I assume that you're in this room because you also love Java, and you probably already know that Java language is designed to be type safe and easy to use. We kind of love that from these two perspectives. And it has many features that provide security benefits, such as memory management, garbage collection, range checking on arrays, access modifiers, right? Just to name a few. And this reduces the overall programming burden on us, the developers, right? But while these changes are easier to notice with each release, especially the language features, there's a question like, but what changed when it comes to security? Sometimes there are JDK enhancement proposals that signal that something major has changed with JDK security, but there are other subtle changes that can impact you in your day-to-day life, hence the talk of today. And speaking of JDK security impact, these are a few things that I would like to name about the JDK security impact. But why should you care is mostly because the support lifetime for a JDK version can span across multiple years, like in the case of JDK 8, which probably some of us are still using. By the way, are people using JDK 8 in the audience? Can you please raise your hand? There's no blame, no shame. It's good. It was a great release, I mean, and it had so many great stuff like lambdas and streams and more. But that JDK release happened a while ago. And not just Java evolved, but also the hackers kind of improved their skills on hacking certain cryptographic algorithms. So the JDK has to also respond to these potential attacks, hence the changes that come with each release, including in security, and especially with security. And today's talk is going to touch a few points about Java security. And I want you to have the good dictionary with you when I'm talking about those things so that you would know to which block from Java security I'm referring to, because this is quite broad. So let's look at the components that we're going to refer to today. Now, Java security consists, of course, of language and runtime security functionality, along with a comprehensive set of APIs and implementations that cover many different areas. Now, the higher level abstractions that you see here are based on the lower layer concepts. And, well, the foundation of Java security, as you can see, first of all, is cryptography. Now, the cryptography component, we call it Java Cryptography Architecture, JCA, or Java Cryptography Extension, JCE, enables you to encrypt and decrypt data, manage keys, sign and authenticate messages, and much more. Now, the PKI component contains APIs and implementations for validating and building certification paths, or certificate chains, if you know that term better. Also talks about storage of keys and certificates. Now, the next component is this acronym here, the GSSAPI Kerberos. Now, this part is the Generic Security Service Application Program Interface. That's what GSSAPI means. And the JDK implementation of GSSAPI, the JDK contains an implementation of GSSAPI called of Kerberos. Of course, we probably know about TLS already, the Transport Layer Security Component, and that we have also APIs for dealing with TLS as well. And a very important part, signed jars, because they allow us to apply digital signature to our jar files to provide data integrity and authenticity of what we're actually building. And then we have also the Java Generic Security Service, the simple authentication and security layer. What's what those acronyms there mean. And these are a series of frameworks and APIs that are used for authentication and authorization. Now, last but not least, the XML signature component is very important because it contains an API and implementation for generating and validating XML signatures. And we have on top there a few tools. Now, the small set of tools that you see here, they help you with setting security policies. So we have Key Tool for managing key stores, keys, and certificates, Jar Signer for signing and verifying jars. And of course, for working with Kerberos, we have this set of tools, Kinit, Klist, and Ktab. In this presentation, we're going to touch the significant changes that occurred in the JDK security. We're not going to touch everything that changed. There's a lot that happened from 17 to 21, but just the most important ones. So hoping that now you have all at hand to go further, let's start with talking about modern cryptographic algorithms and why we need them. As I said in the beginning, over time, most of and all algorithms can be weakened and exploited more easily, right? Now, there are stronger protocols and algorithms that get continuously created that are replacing or providing an alternative to the old ones. Hence, there is an improvement in the JDK. There are larger key sizes in JDK 20 and 21, and this table contains what changed to what in what specific release in the security. Now, larger key sizes provide stronger cryptographic protection for your applications, making it more difficult for attackers to compromise your data. But also, this increases the resilience of the encryption algorithms, hence ensuring confidentiality and integrity of your data in transit or at rest. So that's one part that happened within JDK 20 and 21, like larger key sizes. But we know nowadays that faster computers are being developed, and these computers that have like beta capabilities to processing data, well, they can also do some bad sides, some bad things to our application. Now, quantum computing looks to dramatically change over this time. And well, it can also be used as a weapon in attacks. And it is believed that the current algorithms that our applications are using there can be broken. So in order to respond to such a potential threat, Java 21 release brought also the first post-quantum cryptography algorithms in OpenJDK. Now, there are two cryptography algorithms. There are post-quantum cryptography algorithms. And for the JDK, we prefer and was preferred HSS LMS. Now, HSS LMS, you have what they come from in the slides and what the acronym is standing for. Now, the base of HSS LMS is the Lighton-McCauley one-time signature scheme, where a single private key can only be used to sign one message. And the security of LMS depends only on the security of underlying hash function, which is believed that will not be broken in the development of large-scale quantum computers. Moreover, the Java Security Standard Algorithms name specification has now a new standard algorithm called HSS LMS for signature check. And you have here how you can read an HSS LMS public key from its serialized format using a key factory implementation available with the SAM provider in this case. But moreover, you can also verify the validity of a signature that uses HSS LMS algorithm via the signature implementation within the same provider. So that's the other part of the signature here. These are two important aspects regarding the cryptography algorithms that changed from 17 to 21. However, there were others that were restricted because, well, we spoke about there are introduced more algorithms that are stronger for our applications, but what we do with the other ones that we had before, right? So Java limits or disables the usage of vulnerable algorithms to ensure a robust environment for your applications. And of course, make sure that you're not using them when you're generating your certificates or more. And I want to talk a little bit about a story here. Now, retiring SHA-1. So there's going to be a little history here. Now, secure hash algorithms, that's what SHA stands for, are a family of cryptographic functions that are designed to keep data secured. And obviously, it works by transforming the data using a hash function. Very simple. SHA-1 was often utilized by checksum calculators for file integrity verification. Some while ago, even the versioning systems like Git, Mercurial, and others were using that for checking different revisions, not for security, for checking revisions. But one important aspect of SHA-1 that was in 1995, when I think it was when it appeared, was the collision resistance. That means that the hash function that SHA-1 was using was to produce a unique hash value for each input message, right? And it was said that SHA-1 ensures that two different messages are highly unlikely to produce the same hash value, right? Making it resistant to collision attacks. That was said in the beginning, in 1995. But in 2011, the National Institute of Standards and Technology, NIST, formally said that, well, SHA-1 is not that safe to use. In 2013, also NIST disallowed SHA-1 usage for digital signatures and declared that it should be phased out by 2030. Now we're in 2024, there's still 6 years where SHA-1 could be used, right? Now what happened is that the JDK also kept up with these changes. What happened is changed the default setting for key tool jar signer from using SHA-1 to use SHA-2. Then SHA-1 was disabled in the TLS server certificates and XML signatures. So gradually, SHA-1 was not the default used within the JDK. But what happened much more dramatically in 2017 is that researchers demonstrated practical collision attacks against SHA-1 cryptographic hash functions. So what was initially said in 95 that makes SHA-1 so great, the resistance to collision attacks, was not anymore the case. In consequences, all major web browsers, what they did, well, they said, we're not going to accept any more SHA-1 SSL certificates. So why am I telling you this in 2024, like 7 years later? Well, SHA-1 was restricted throughout time. However, there were still cases when jars could be signed with SHA-1, even though that now the SHA-2 became the default when signing jars. Even though that you can probably read that's not okay to use this, it's forbidden and so on, jars could still be signed with SHA-1 algorithms. And in order to address this kind of usage, in JDK 18, there was a change that disabled those by default. What this means is that if you're signing a jar with SHA-1, if you're trying to attempt that, that actually would be treated as an unsigned jar in the end. This constraint applies only for jars that were time-stamped after 1st of January 2019. So if a jar was signed before 1st of January 2019, it will not be affected by this change. However, throughout the years, what was recommended was not to use any more SHA-1, to resign your jars with another cryptographic algorithm like SHA-2, SHA-3, and try to avoid this as much as possible. This change was also backported to JDK 17, 11, and 8, what you see there, the little red there. So sometimes the changes that occur in the JDK security are also backported, even if they occur at a later release in time. It's very important for people that are not yet able to migrate to the latest release. Other important aspects about JDK cryptographic algorithms. Now, TLS algorithms were also, the weak ones were also disabled. What this means is that the 3-DES cipher suits have been removed from the default enabled TLS cipher suits as of JDK 19. There's 3-DES and and ARC4 and other algorithms that are not anymore enabled since JDK 20 because they do not preserve forward secrecy and are rarely used in practice. So there were like two meanings for that. And also, we have a change like the TLS 1.0 and TLS 1.1 were also disabled by default since April 2021. But there was also another change that applications should be using more DTLS 1.2 protocol and not use DTLS 1.0. Other restriction rules to weak algorithms were for Kerberos. Now, Kerberos is the protocol for authenticating service requests between trusted hosts across an untrusted network, such as internet. And probably if you encountered the term Kerberos, if you ever have configured an application server, that used to use a little bit more the Kerberos terminology. But the configuration for Kerberos is in a krb5.conf file. And that's where you can add restriction rules for your weak algorithms. What happened is that DES, 3-DES, ARC4 have been removed from the default list of Kerberos encryption types. However, they're already disabled prior to the release of JDK 18, and would not be used. But what you can do if you really, really need them, you can use the allow weak crypto property and that what people were doing, they were setting the allow weak crypto to true in order to use those algorithms because they needed them in their configuration. And what I show you here in this slide is how you can selectively enable weak algorithms. So the way to do it, the best way to do it, was actually to enable weak algorithms selectively if your configuration really needs it, like by keeping allow weak crypto to false and say which permitted encryption types are allowed even if they're weak. So that's what you can do if you really need to use those weak encryption types, because if you're setting the allow weak crypto to true, that's going to allow all the bad encryption types to be used in your application. So that's one good thing that came with this change. But moreover, I want to emphasize some change that, well, re-enabling any weak encryption type is not recommended. And if you do that, you are kind of on your own. I mean, your application is kind of on your own in terms of attacks. And I realize now that probably you've heard about a very, very important change that occurred in JDK 17 with security manager. Who here has heard that the security manager was deprecated for removal? 1, 2, 3, 4. Okay. Okay. So the security manager, just to give you some context, is a feature that was originally designed as a sandbox for running potentially untrusted applets. Do you remember applets? Okay. So that was its purpose. But later was enhanced to support a fine-grained permission model, and still was not that widely used. So a lot of people, when they heard that security manager is deprecated for removal, is a bad thing that's going to impact the world, is going to stop us all. What happened is that it was not that widely used, in fact. And moreover, it kind of meant that it should be taken off and deprecated for removal because it had a brittle permission model. We have probably not used applets as developers for a long, long time, since now we have better frameworks at hand that we can develop web applications with. Also, it had a difficult programming model and a poor performance. However, if any applications were still using the security manager, that one still is available, but is available in JDK 17. But starting with 18, there is a property that has disallow us the default value for the security manager. Now, the reason why I'm telling you about this is not that there was a feature that was deprecated for removal, and as I said, was not that widely used by developers in the real life, but it had some implications internally for the JDK because there were some APIs that depended on the security manager. Hence, some security APIs enhancements were necessary on that so that there's no more dependency on the security manager. And let's take this code example for now. Well, JDK 17 deprecated for removal the security manager. And as part of this change, there were several security manager APIs that were deprecated for removal, like access control context that you see in the slide. So access control context was also subject of the deprecation for removal. This means that if you need access to like in this case, to the subject, you had to go through the access control context. And what to do in this case, you need a different way to access that. So that spawned a new change in JDK 18 for the JAS APIs. When would you use such an API? This API is important when you want to write secure application that authorize subjects or perform sensitive operation based on the subject's credential. So how this got rewritten? It got rewritten to use another API to getting the current subject. So before, to get the current subject, you had to get the access control object, and then based on the access control object, you used to get subject and get the subject there. So no more intermediary object need to access the current subject. There was another improvement in JDK 18 about the key store attributes access. So before JDK 18, the way that you could get access to the attributes of a certain entry in a key store, you could have done that if you are calling get attributes on the method key store point entry. And if this entry was a private key, the application needed also to provide the proper password to unlock that specific entry, even if the attributes were not necessarily password protected. So in the new API, there is no need for the extra hoop to get also the password, not just the alias, just to get the attributes of a specific entry in a key store. You just use key store get attributes based on that name of the alias of that key, and you get the value, you get the attributes there. So no need to know the password anymore. Less objects using this in this operation as well. Moreover, there is a way now to customize TLS and DTLS name groups. So if you want to restrict the name groups that your application is using in TLS handshakes, you can do that now with a set of methods that are providing access to that through this SSL parameters via the set name groups. And of course, there's also a get name groups associated to that. There's also a way to customize TLS and DTLS signature schemes. Now there's a set signature schemes and a get signature schemes available in the API's SSL parameters as well, starting with JDK 19. And going back to the quantum computers, we have a new API that is securing symmetric keys using public key cryptography, and that is called Key Encapsulation Mechanism API. In JDK 21, this Key Encapsulation Mechanism API became available, was a JEP on it. And it's also a scheme, as I said, with public and private keys, where the sender uses the public key to create a ciphertext, a so-called encapsulation, containing a randomly chosen symmetric key, and the receiver decrypts the encapsulation with a private key. What makes it so unique is that, unlike traditional cryptography methods, a key encapsulation mechanism does not require padding because it uses properties of the public key to derive a related symmetric key. So these are just a few properties of it. Let's see it a little bit in action. So what happens? This sender creates an encapsulation using the public key. Then the sender is using KEM to transmit the shared key to the receiver. Later, the sender can also use KEM to encrypt data using a symmetric key algorithm. And the receiver decrypts the encapsulation, of course, with a private key that they already have. So what I might want to say in this part, that you can use SCAM to first transmit the shared symmetric key and later use it to encrypt data using a symmetric algorithm. Now, key encapsulation mechanism API components has a few parts. There's a key pair generation function. There was no new enhancement there. There's still the use of key pair generator API that we probably already know. There was a change on introducing a key encapsulation that encapsulates the public key and, of course, returns the key encapsulation message and the shared secret. And, of course, there's a key decapsulation API part that encapsulates, using the private key, the encapsulation message, and it should result also to the shared secret. Now, in JDK 23, there are going to be some more developments about CAM, and I've recently seen a job around that. And probably I'm going to talk a little bit at the end. There's time. What else changed besides APIs? There was also some improvements at the OS-specific level. So there are specific features in the JDK that are typically dedicated to operating systems, and they function only for a specific operating system, like Windows, Mac OS, and so on. Now, if you are using Windows servers or Windows machines, Windows stores keys and certificates for either current user or the local machine. And sometimes you might need to access them, right? So ideally, you do that using a provider like Sun MSC API provider to access the native cryptographic libraries, certificate stores, and others. Now, in that case, only the certificates available to some users' accounts are listed. So what happened is that a new change was introduced to get access to the only user accounts certificates using a new name of key store type called Windows My Current User. So there are new key store types called Windows My Local Machine and Windows My Current User that were added in JDK 19 to provide access to keys and certificates stored in the Windows operating systems that are available to all accounts. Now, there are also some new names, like to avoid confusion, like Windows My Current User and Windows Root Current User names have been introduced, and they map to Windows My and Windows Root that were used previously in the documentation. All these changes are documented in the JDK Providers User Guide, by the way, so it's up there. And at the end, I'm going to provide the links to that. Now, this is more close to my heart because I'm a Mac user, and I could probably demonstrate this one. There are a few changes with the macOS keychain store. So before JDK 21, only the user domain was considered when displaying the key store contents of a macOS keychains. But starting with JDK 21, the macOS keychain store implementation exposes certificates with proper trust, user domain, admin domain, or more. And just to show you a difference on that, let me show you a small application here. So here's my main application that gets an instance to the keychain store for the provider Apple, which is for my computer. I'm not using any password or something. And I just want to see the certificates that I have on my system. Now, if I'm going to the command line and just say Java 20, and now let's run this Java source main Java org example main.java. This tells me that I have access to 6 certificates in the key store chain, right? Let's clear this. Let's change to Java 21. Run it again. Now I get the answer that, so let me make this a little bit bigger. The size is actually 11. So that's the change that happened with the access to the underlying certificates in my key store. The reason is because my user on my computer that I use to run these commands is actually also having rights of admin. So I have rights to see more certificates, not just those 6 that I saw earlier for my user domain. Apart from these changes for the macOS Keychain Store, there were also some updates for the JDK kcerts file. Have you used kcerts? Can you please raise your hand? Well, what was its default password all the time? Change it, right? We have used to change it, and we kind of, I think it's became in our DNA as developers to always use kcerts to change it. Now, the good news is there's no more passwords for that. So there's no longer need to specify that, thank God. And you can use kcerts without that. But moreover, public certificates are no longer encrypted. I mean, there were public certificates. There was no need for being encrypted anyway. So another good thing about it, it's not using JKS format anymore. So there's no more proprietary format. It uses PKCS12, which is a widely used format, and you probably know that for more time. And I remember, but back in the day, I used to transform from PKCS to JKS because that's the way to do things, and so on. So no more that. That's really, really great. So this is what briefly changed from 17 to 21 with kcerts, and I think it's great. So no more password, uses a format that is widely used. And, well, the public certificates are no longer encrypted. But moreover than this, there is also no MAC integrity check needed. So that's why you don't need to use the change it anymore. But if you decide to store sensitive information in your kcerts, you do need to provide a password. So that is still recommended. No change it, but you still have to provide a password if you're going to store anything sensitive in it. Now, what happened with the tools? In the beginning, I mentioned that there are some tools that the JDK, or that security tools that JDK Security is concerned with. And the evolution of Java Security API has fostered also a deeper connection with the tools, but also with the monitoring tools. So the key tool improvements, the main ones, since there are larger default key sizes, of course, that gets also when we are using them with generating them with key tool. So when we're using -Janky pair or we're using -Janky pair without any key size specified, then that the default size is going to be the larger one. It's not, of course, if you're using key size, you can also increase that one. No more 2048, for example. For RSA, you can also go to 3072. Next, the -gensec key and import pass options warn you if there is a weak password-based encrypted algorithm, like in the case of ARC4 in this example here. So in this small example, when I run key tool with a -gensec key, like generate for me a security key, a secret key with ARC4, what I get back is a warning that I'm trying to actually use an algorithm that is weak. And that is being done based on the -key alg option that is getting evaluated by gensec key when that is being ran. Moreover, for jar signer, we talked about the fact that, well, if you're trying to sign a jar with SHA-1, that's going to be disabled by default, and the jar is going to be treated as unsigned. But some other improvements came to it as well. The default digest and signature algorithms are strengthened, and you can also specify now a class path for an alternate key store implementation via -provider path. Like, for example, starting with JDK 19, you can run this command and also say your own provider path. I said there test MIHALCEANU, but you can give your own key store as provider path for signing your jars. Oh, there's something else that I need to tell you about. We're still at security. I said about improvements with the monitoring tools, right? So JFR, for example, has a few security events that get captured about your application and its underlying JVM. Now, JDK Flight Recorder tool provides you two default configurations. Let me just go with Java 21 here. And a few things have changed since 17 to 21 with those events as well. I'm going to copy it so that I can see it locally. So let's copy the default configuration from Java Home. Where was that? Lib, I think. Yeah, Java Home, lib, JFR. Yes. So I want to copy the default configuration just to look at it and see what changed here. In JDK 12, when JFR was no longer proprietary and became part of the JDK tools, there were a few, there were a few events that concerned security that became available for you to investigate. Among these security events, let me see if this helps me. Okay, JDK TLS handshake. Yeah. So among the security properties that were available starting with JDK 12 was JDK TLS handshake that was telling you if a successful TLS handshake was negotiated and what was involved in that, disabled by default, as you can see here. There are two events concerning the details and validation of the digital certificates X509, and they were also disabled by default. But there was also an event called security property modification, disabled by default as well, that was looking over the Java security invocations, over changing dynamically the security properties for your application. So these were starting with JDK 12. However, folks looked a little bit at it and said, like, maybe if we're monitoring these events regarding the JVM and security of a Java application, it would be good to have a starting point for our Java applications as well, like to have the initial security property. So in JDK 20, the JDK initial security property became available, is enabled by default. So the only security property that's enabled by default in the default.gfc and profile.gfc file. And in addition to this one, you can also check the security provider service invocation with the JDK security provider service. So in JDK 20, there were two of them that became available to investigate more about the initial security properties and the provider service invocation. The first one, while it's enabled by default, this one is disabled by default. You can enable it in your profile using JFR, or you just copy the profile and edit the XML, like I could do it here as well. So these are some changes about this about the security, the JFR security events. Another important thing is that you can look at these events with a new command that came up with JDK 21, the GFR view command. So you can also look at these events and inspect how these events have evolved with GFR view, starting with JDK 21. And apart from these changes, these changes are being selected based on a specific path. They are not randomly chosen. They're evolved. So the evolution of the JDK security is done in a very transparent way, and you can find that by going to the Java crypto roadmap. So this is the location where you can find all the details on how the JDK security has evolved in the past years. And that page is getting continuously updated because, well, things change very fast, especially with security. And this was created to inform everybody about the coming security changes in the update releases. Now, this java.com crypto roadmap, it concerns most of the time JDK security changes for the Oracle JDK release. However, other vendors also have their own crypto roadmap that most of the time aligns with this one. Is because, especially when it comes to restricting algorithms, it's better to be prepared. Now, each change in this crypto roadmap improves security in a certain way. So you can find there when an algorithm is going to be restricted or disabled, or where you can find there if a default has been changed to be stronger, or you can find there all the details about the support for stronger algorithms that was created, or if the tools that help you to diagnose security problems have been improved. So everything is being documented there in a very nice table. However, because these changes can be sometimes disruptive and can put some compatibility risk within your applications, these changes also include testing instructions and details on how you can revert the change, of course, if possible. So this is also given in advance notice, except in the case of a severe vulnerability. It's not just changed out of the blue during the night and it gets up there in the JDK. Apart from this, there are some other places where you can stay tuned for more information about Java security and not only. So we have a few places within the Java DevRel group where you can find what's going on with Java overall, not just security. Dev.java provides for you tutorials about how to use certain parts of Java. Inside.java provides the latest news, so it's like a news aggregator, what's going on, like which jobs are targeting now JDK 23, for example, or if there is some news, like it was the unfortunate case of Apple with M1 chips that was terminating Java. So all these things are usually published here, and you can get the latest notice here as well on Inside Java. But also there are research articles, blog posts from the engineers, and more. Also, we have a YouTube channel, the Java channel, where we publish videos on security, on garbage collectors, like you see here, are also on using language features and more. So we have different formats, like a lengthier formats, like JEP cafes, that look into details of a certain JEP and explain that in a more digestible format on how you could use the contents of that specific JEP in the future, or in the news format, like the newscast, and give you like information, hey, this is a cool thing is going to happen next within the JDK. And this is how it was going to benefit you in your day-to-day life. So we have all these places where you can get more information about what's going on in Java. And of course, there are a set of useful links that I got together because I've used them probably in the presentation or made a reference to it in the presentation. There's a lengthier video that has more details about what happened with the security between 2017 and 21 that was published last year before the live stream of Java 21. And of course, the link to crypto roadmap, security standard algorithm names, and a very useful blog that Sean Mullen is keeping up about the JDK security changes. This presentation also, I'm very grateful to my colleagues Sean Mullen and Wei-Jung Wang that have reviewed it and give me feedback upon it. And they're very, very helpful all the time in responding about security changes within the JDK. So without further ado, I want to thank you. This is where you can find the slides, a little bit more detailed than what I showed you today. And I'm welcoming questions from your side now. Thanks.